sound quality and timbre. Normally, when you plug a guitar string, you cannot form only one standing wave at a time. Sometimes in the strings it's possible more than one harmonic can be formed. I mean, first and second harmonic, third harmonic together at the same time can occur at different strings as well. There are many strings, and that's why you cannot control that one. In the string, you can do experiment and you can control which harmonic can be present. But in guitar string, you plug the string, you release the string free. String is free, so that's why more than one harmonic at the same time can be present, can be obtained from the strings of a guitar. So that's why your book is starting with this. When you plug a string, a variety of the standing waves can occur when string is set into vibration, more than one standing wave at one time. Sound waves from an instrument actually consist of multiple frequencies, multiple harmonics. So mixture of all these harmonics produces characteristic sound of an instrument, which is called as sound quality and timbre. That's why when you play same note with two different instruments, like one of them is the violin, the other one is guitar, but both are playing same notes. I mean, are they giving the same sound to us? Reason is that, because their harmonics are, the intensity of their harmonics are different. Yani mixture of harmonics are different for each instrument. Even they play the same notes, so their sound quality, mixture of harmonics are different. So the first device we studied was a tuning fork. Remember, tuning fork was vibrating with simple harmonic motion. That's why its waveform was a sine wave. It was like this. But other instruments are not vibrating with simple harmonic motion. Even there are more than one string, they can vibrate at different frequencies. So that's why their sound is a mixture of harmonics. For example, these are two instruments. One of them is clarinet. I think clarinet is given in your book. Clarinet vibrates at different harmonics at different intensities. For example, third harmonic is most intense. After that, first harmonic is second intense. Second harmonic is least intense. Fourth, fifth, and seventh also a little observable intensity. So when all these harmonics are mixed, we get a wave. This is the waveform of a clarinet. You are going to combine the first, second, third, all these harmonics will be combined and you will get the resultant waveform. This resultant waveform belongs to a clarinet. This is tuning fork. Tuning fork is only vibrating at the first harmonic. That's why simple waveform. But for a clarinet, for a violin, for a guitar, so waveforms are a little complex, very complex compared to a tuning fork. So other instruments vibrate at different frequencies, first, second, third, fourth, fifth, seventh, and so on, at different intensities. Look at their intensities different. There are multiple harmonics in an instrument, not only one harmonic at the same time. Each harmonic is a sine wave, correct, like this one. Like this one, each harmonic is a sine wave. First harmonic, second harmonic, third harmonic, but their resultant is complex. When we combine all these harmonics, resultant waveform becomes a complex waveform. Each harmonic is a sine wave, but when available harmonics are added together, according to the principle of superposition, they give a resultant waveform, which is complex waveform, like this one. However, even if they are complex, you see that they are repeating each other. For example, from here to there, or 1 to position 2, from 2 to 3, from 3 to 4, from 4 to 5, they are repeating each other. You see that? Repeating waveform. Such waveforms of every instrument consist repeating patterns, which makes the music. Music is repeating patterns, in fact. Such waveforms are called periodic. We know that if something repeats itself, that is called periodic. So this waveform is complex but periodic waveform. It is the same for all instruments. I mean, clarinet is given in your book. That's why I put only clarinet. Violin, guitar, all they have different shapes, complex shapes, but all they have repeating patterns. All they have periodic waveforms. And that's why question says generally fundamental frequency determines the pitch. You are going to hear from an instrument generally when the instrument is played. Dominant one is going to be the one which is the first harmonic. Generally, first harmonic will be dominant, but at the same time, some strings can vibrate second harmonic, can third, but their intensity will be low, and that's why they will not determine, or we are not going to hear the other harmonics as the more intense sound. Generally, you are going to detect the more intense one, which is again fundamental frequency. There are also other harmonics, as I said, second harmonic, third harmonic, fourth harmonic can vibrate on other strings. These harmonics, second, third, fourth, and are called overtones in musical literature. Yani second harmonic is sometimes called first overtone, third harmonic is called second overtone, fourth harmonic is called third overtone, and so on. In music, I don't know why they said they give such a number. So first overtone, second overtone, so third overtone, fourth overtone, second harmonic is first overtone, third harmonic is second overtone, fourth harmonic is third overtone, and so on. It's going like this. In a chromatic musical scale, they say that there are 12 notes. There are 12 notes in a chromatic musical scale. But frequency of the 13th note is exactly twice that of the first note. For example, first note is A. Its frequency is 440. 13th note will be A again, but will belong to second harmonic or first overtone. Its frequencies will be twice of that. Yani 440 multiplied by 2 is going to be 880. This interval in music is called 1 octave. 1 octave. Yani frequency of the 13th note is exactly twice of the first note. Altogether, yani 12 plus 13th note altogether form an octave according to music literature. Repetitive echo of a sound from ceilings, wall, floor, and other surfaces is called reverberation. For example, when you enter a room which is empty and talk, so you see your sound is echoing continuously. But if you put the things inside this room, like curtains, like some furnitures, sound does not reflect. So reverberation is reflection of the sound from the surfaces. It's called reverberation. For example, in Turkey, reverberation is very strong in the mosques. When somebody is talking in some corner, because there are the walls and the ceilings are a little curved, it gives the reflection, and then you can even hear somebody which is whispering on the other corner of the mosque. But some places you need more reverberation. In the past, there was no microphone. When the Imam was talking, everybody should hear. That's why in the mosques constructed earlier is reverberation is very strong. But in an auditorium or a concert hall, reverberation mustn't be. So there mustn't be any reflection. To stop the reflection, you should cover the walls and then of a room with soft materials. This is a radio studio. You see the walls? These walls are not reflecting the sound, because in the studios you should stop reflection. Otherwise, echoing can make the sound worse. So For speech to be clearly heard, reverberation time, yani reflection of the sound in the auditorium in a studio must be really small, and time that must be, and the sound must be observed by the wall. Ceilings in the library, other quiet places are often made of soft and textured material to absorb the sound. Or padded furnishing, plants also absorbs the sound, decrease reverberation. So here's a movie about this. Watch this movie. In the first room, it is perfect reflection. Walls are not covered. This perfect reflection.
I'm in the reverberation chamber at the University of Edinburgh. Here, the walls and the ceiling are all hard plastered to give maximum sound reflection. Note that none of the surfaces are parallel. This is to avoid standing waves being set up within the space. When I speak to you, what you are hearing is the direct sound from my mouth, together with multiple reflections from the walls, the ceiling,
So
and
sound
the
is reflecting
floor.
from the
Is
ceilings and then
sound
all
clear
mixed
at
together,
all?
and then you cannot hear. Reverberation is
Effectively,
maximum.
the sound is homogeneous and isotropic throughout the space.
But now he's going to speak in a room which is
I've come through now to the anechoic chamber. Anechoic
almost zero
means
reflection.
non-echoing. The walls, the ceiling, and even the floor in this chamber are lined with foam wedges which absorb the sound. So the room's almost free from reflections. When I'm speaking, all you're hearing is the direct sound from my mouth.
You don't hear the reflection, you only see
You
direct.
can hear the sound is much clearer than in the reverberation chamber next door. But correspondingly, the overall sound level is much less.
So this is the difference. In the first room, reverberation was very strong, reflection, echoing is very strong. But in the second room, because walls are covered with sponge, with some textured materials, so they absorb the sound, they don't reflect it. So you hear only direct sound coming from the mouth of that man.